Okay, in this second session of our lecture, we will try to finish our rush through the most fundamental concepts and the two most important statements of classical probability theory. The concepts we want to discuss are the concepts of an expectation value of a random variable, its variance and its importance as a measure for the probability of deviation from the mean. And then we will discuss the law of large numbers in weak form, and we will present without proof the central limit theorem, which tells us that the standard normal distribution of the Gaussian distribution is a natural phenomenon in nature. Okay, let's get started with the concept of the expected value of a random variable. Let's start with an example. Suppose we want to bet on the sequence of three numbers which are generated by a random number generator. The random number generator, each time we hit it, produces a number among 1, 2, and 3. So 1, 2, or 3 are selected in an unbiased fashion each round. We use the random number generator. And we want to use it now 3 times to generate a sequence of 3 numbers, where each of the numbers can be 1, 2, or 3. And then we want to bet on the outcome of this triple by betting on the sum of the 3 sampled numbers. So in other words, we ask someone to give us as a payoff the sum of the 3 numbers that the random number generator produced in those 3 rounds. This means that we can have a minimal payoff of €3, and we can have a maximal payoff of €9, depending on the 3 realizations of these random numbers that were drawn by the random number generator. If we find someone who is willing to grant this payment, and if that person on the other side behaves like a rational person, then this person should ask for a price that we have to pay for this game. And the question is, what would be a fair or a rational price for this game? What is a rational price for this game to be played? And one reasonable and intuitive answer is that a rational price for this game would be something like the mean of the payoffs that can be realized. But however, it should not be the plain arithmetic mean of these payoffs. It should be a mean which is weighted according to the probability of the individual payoff. In order to compute that mean payoff, which is weighted according to probability, we have to compute the probability of each individual payoff. Now, as I said before, the payoff of €3 can be realized only if the 3 sampled numbers are each equal to 1. So the triple that is generated is the triple 1, 1, 1. There are 27 possible triples. Each of them has the same probability, so the probability to sample exactly this one triple, which generates payoff 3, is 1 over 27. The same with 9. So the payoff 9 is only given when the 3 sampled numbers equal 3 each. That's again one specific triple among all 27 possible triples, and therefore the probability of that payoff is 1 over 27. The payoff with the maximal numbers of possibilities of triples which generate that outcome is the number 6, which has 7 triples. And therefore the probability of a payoff of €6 under this bet is 7 over 27. Hence, if we compute the mean payoff, but mean in the weighted sense, we have to compute the following number. We compute 3 as payoff, multiplied by its probability, which is 1 over 27. The payoff 4 appears with probability 3 over 27. The payoff 6 with probability 7 over 27, and so forth. We sum up all these numbers, and if we do it right, and if we didn't do any wrong computations, then this is 172 over 27, which is 6.37. So a rational price for this bet would be probably €6.37 if you think that this mean is an intuitive and right quantity. We will see at the end of this session that this is in fact a good answer. Now what we computed here in fact is what we call in probability theory the expected value of this bet x. If we understand this bet that we played as an instance of the concept of a random variable with integer or real outcome. Okay, in order to introduce this concept of an expected value, we will consider first the special case that we deal with so-called simple random variables. Recall that the object that we have just discussed, namely this bet, is nothing but a random variable because it converts the outcome of the random experiment, which is the 3 hits or the 3 rounds of using the random number generator, so the output, which then is nothing but a random triple of points, of numbers, it converts this random triple into an output through the assignment that the triple is mapped onto the sum of its entries. So this is this bet or this payoff function is what we called a random variable. And now we want to introduce the concept of the expected value for random variables which are simple. What is a simple or elementary random variable? So a random variable x is called simple or elementary if x assumes only finitely many values, which could be phrased like this: if we just consider the range of all values which are assumed under the map X, then this collection or this set should be a set of finite cardinality. And if that's the case, then we call this random variable simple. And in this case, we have a simple concept of what we would call the mean value. If we denote by Rk the collection of real values that this real valued random variable assumes, then we compute exactly the object that we computed before and the example that we considered before. We compute the sum of all possible outputs or all possible points in the range of this random variable x, where we multiply each output by the probability that this output is actually generated. This is what we would call the expected, or what we will call the expected value or the mean of the random variable x. And if you look at the sum that we have just computed in the example before, you see in fact that we did nothing but compute this expected value. Now look at this from a kind of schematic, geometric point of view. If a random variable is simple, then we can decompose the space of all realizations, or the set of all realizations, into those subsets which are the corresponding pre-images of those finitely many image points. So since there are only finitely many image points under the map X, the set omega can be decomposed in finitely many pre-image sets corresponding to the corresponding values. Here in this case, in this picture, I have drawn such a decomposition in the case when the random variable x assumes only 3 values. Of course, the decomposition of omega into such subsets does not need to be as nice as in this picture, when you have these very compact and not scattered and connected, so to say, regions of omega. It may be much more scattered. But nevertheless, we have a decomposition, a unique and a clear decomposition of omega into finitely many subsets. And then this expected value, which we have just introduced, as we had written it before in this case, would be just this product, or this sum of products, where we multiply the image value of the random variable with the size of its pre-image, where we measure this pre-image, omega 1, in the case of R1, we measure it using our probability measure P as a size, as an object to measure the size of a set. And we do this for all possible values that the random variable x can assume. So we multiply each time a number which we consider as a height, and we multiply this height with a size. So in another representation of geometric interpretation, what we do is we decompose the space omega, or the set omega, into these subsets where the function x, if we consider it as a function, is piecewise constant, and then this sum here above corresponds to taking the sum of all these areas which are obtained as a product of a certain, as a product of the size of the base set multiplied with the height of the corresponding subgraph, or the corresponding block, so to say. So in the end, we have nothing but a sum of different volumes, where volume or area, depending on the dimension in which you want to consider this picture, where the area or volume of each of those blocks is just the product of the area of the respective subset. That's the area, and it's multiplied by the height, where the height is just the value of the function on this subset, where the function x is constant. So we see that this expected value has the natural interpretation of a volume, or is the integral, in fact, of a piecewise constant function, where on the domain space, in the vertical, in the horizontal dimension, an omega, we measure sizes of sets using the p function. And therefore we can interpret and write even, in fact, this expected value which we had just introduced as the integral of the random variable x over the space omega when we integrate with respect to the probability measure p. The geometric interpretation of the expected value for a simple random variable as an integral is in fact the basis for the following general definition of expected value for a random variable which might not be simple and which might have infinitely many possible outcomes, or even uncountably many outcomes. Provided we have a measurable real-valued random variable, then we can talk about the expectation as an integral, because then we can use the standard theory of integration from analysis. We have, in this case, everything we need for the definition of an integral, which we import from analysis. So we have a certain space omega, we have a measurable function x of omega, which maps from omega into the real numbers, and we have a measure on this space omega, which is the probability measure. So therefore, we can define for a real-valued random variable the expected value as the integral of x over omega with respect to the probability measure p. This is what we would call, or what we will call in the future, the expected value of x. Sometimes we call this also the mean. And another remark regarding this definition is that since the integral operation just needs to allow for linear combinations of the outputs of x, we could also straight away generalize this definition of a mean to random variables which assume values in a vector space, because then we can perform this linear combination of output values. So the integral that we have here can either be understood as a concept of a volume under the graph of the function x, or it can be understood as a linear combination of which is then a weighted mean value of the corresponding outputs of the function x. Both interpretations are good and equally useful. The following consideration shows that the expected value of a random variable depends only on its law. In order to see this, we consider the general transformation rule for integrals, which I want to present now. So this general transformation rule applies to the situation that you have a random variable, x, which maps from your given probability space to another measurable space, and then you transform yet another time the results of the random variable x by a real valued function f, which maps the combined outcome of this random experiment, which is parameterized by omega, into the reals. So if f is a measurable function, which means it is a measurable map, as we discussed before, from the space S equipped with its sigma algebra sigma, say, into the reals, which we, if we do not specify otherwise, always equipped with the Borel sigma algebra. So if this function f is measurable, then the composition of x with this second function f gives rise to a new random variable z, which in the end is a random variable which maps from omega to the reals. So that's the random variable z. Since this is now a real valued random variable, we can talk about the expectation of z. And the statement of this general transformation rule is as follows. So the expectation of this new real valued random variable z, which is by definition just the expectation of this combined composition of f acting on x, or in other words, it's just this integral as we had just defined. This can in fact be evaluated by performing an integral not on omega, but on the intermediate space S, using just the law of the random variable x. That's the general transformation rule that we will work with in the future. It says that if you have a combined random variable which is obtained as an abstract random variable which maps into an abstract space set S, an abstract space S, and if this abstract random variable is then converted by another function into a real valued random variable, then the expectation of this combined random variable can be computed by performing an integral on the intermediate space, where on the intermediate space you have to use a specific measure, namely the law of the random variable x. So the push forward measure of the p measure on omega, which is then pushed forward under x to generate what we called the law of x on S. So that's the statement. If you want to compute this combined probability and the combined expectation of, or the expectation of this combined random variable, all you need is to do an expectation, or to compute an integral, in fact, on this intermediate space. Why is this statement correct? So what would be a first explanation why such a statement could be true? Well, in such a situation, when you have a statement coming from measure theory or from integration theory, one thing that you should always try to do first is to check whether the statement makes sense in a simplified situation when you use very simple random variables or simple functions. And one of the simplest functions we could choose for f as a check, as a sanity check, is when f is just an indicator function. So example, f is just an indicator function of some set curly S, which is in the sigma algebra sigma on the state space S. Then you see that this statement, which is claimed here, is nothing but a restatement or rephrasing the definition of the push-forward measure, because it means that the computation of an indicator function, or the integral of an indicator function, just means that you compute the size of the measure, you compute the measure of the set to which the indicator function belongs. But then on the right-hand side, you just ask for the measure of the law of the random variable x on the subset curly S, and by definition this is just the indicator of the pre-image integrated against the measure p. And if you put those things together, you will see immediately that this is nothing but the straightforward interpretation or the straightforward definition of the law of x. And then for more general functions than just indicator functions, so for more general cases when f is not necessarily an indicator function, this statement will follow just by approximation. Okay, so we see that computing the expectation in many cases of a transformation of a random variable just involves the law of the random variable on this intermediate space. We can use this now in order to convince ourselves that the expected value of a real valued random variable depends only on the law of the random variable. Why so? Well, the formula here is like this. The expected value of a random variable can be obtained by just integrating the function, the x function, the identity function on the real line, when you integrate this against the law of the random variable x. And why is this so? Well, you apply the previous scheme to the case when the intermediate space is in fact just the real line. So when x itself is real valued, then already the space S is the real space, is the real line. And as function f, you choose just the identity function. If you do this, you obtain that the expected value of x is just the previous statement. The expected value of x is just the transformation of the random variable x using the map f, in this case as identity, the identity map f. And then this previous statement just tells you that this needs to be the identity function, so the f function x, integrated on the image set S, which is the real line here, integrated against the law, which was eta. So you see that the expected value of a random variable depends only on the law of this random variable. It's completely irrelevant of what kind the initial probability space omega was, provided you have access to the law of the random variable. If you know that, you can compute its expected value. Let us consider an example, namely let's consider the expected value of a random variable which is distributed according to a standard normal Gaussian distribution. So we know that the probability for the random variable x to assume values in a certain subset E of the real line is given by the area of the region which is bound by E and the graph of the Gaussian bell-shaped function. So the probability that the random variable, wherever it was coming from, or however it is generated, the probability that the random variable assumes values in the set E is given exactly by this new, not 1 of E. Okay, so suppose we have a random variable whose law is the standard normal distribution. Then we can compute its expected value. I claim that the expected value in this case is 0. Why? Because we integrate the identity function x against this weight function e to the minus u squared dx. The identity function x is anti-symmetric. This function here, the bell-shaped function, is symmetric. And if you compute the integral of f of x, g of x, dx over the entire real line, when f is symmetric, or anti-symmetric, say, and g is symmetric, by simple symmetry consideration, you find that this integral must be 0. So this explains why the expected value of a Gaussian, standard normal Gaussian, is 0. By the way, we can also mention that the expected value of a probability measure on the real line corresponds to the center of mass of the corresponding geometric shape. And obviously, if you have a symmetric shape, which is symmetrically placed at the origin, towards the origin, then the center of mass should also be the origin. We can also compute now the expected value of the square of the same random variable, because this is just the transformation of the random variable x using the square function. So this is the expectation of the random variable x, but transformed with a function f, which in this case would be the square function on the real line. So just a standard parabola. By our previous formula, this is just the integral of that function, which in our case is the square function, with respect to the law of the standard normal. The law of the standard normal is the weighted Lebesgue measure, with the weight function given by the Gauss bell-shaped function. And this is now an integral which we can compute by a little trick, because we write this x squared factor as a product of x times x. And we see that the second part here is, by chain rule, the derivative of the function e to the minus x squared, minus of that, if you like. And so we can apply integration by parts to compute the integral by mapping the derivative here in this integration towards the other component, which generates then the derivative of this x function in the remaining integral, which is just a 1, and what remains is just this integral over the Gauss curve, but the prefactor of the Gauss curve is chosen in such a fashion that the total integral equals exactly this prefactor, or in other words, that this integral altogether is just a plain 1, and the first part, using the fact that the exponential function dominates every polynomial, is identified as 0. So we have seen that for a standard normal distributed random variable, we find that the expectation is 0, and the expectation of that same random variable squared is 1. Okay. That was an example how to compute the expected value of a random variable when you have access to the law of that random variable, or in other words, to compute the expected value of a random variable. Sometimes it's useful just to do it using the law. Now, since we know, or since we have defined the expected value as an integral of this real valued function, which is defined on the space omega, it enjoys the same properties as the conventional integral that we know from classical one, or from the classical Lebesgue integral on Euclidean space or in higher dimension, although our concept of integral is slightly more general. Namely, the expected value is linear in the sense that if you have a random variable which is the combination, a linear combination of two random variables, x and y, with coefficients lambda and mu from the reals, then this expected value behaves as a linear operation. So the expected value of a linear combination is the same as the linear combination of the expected values. Then if one random variable dominates the other, so in terms of bets, if one bet is so that it dominates another bet, or in other words, one bet always leads to higher payoff than the other bet, then the same relation is true for the corresponding means or payoffs. And finally, we have what is called the Jensen's inequality, which says that if you have a convex function on the real line, then you can compute the expected value of a random variable and apply the convex function, or you can first apply the convex function to the random variable and then compute the expected value. And the second operation gives the higher value. Well, why is this so? Well, a convex function has the property that the convex function evaluated at the average of 2 points is less than the average of the convex function. And what we see here is exactly this. So here we have the convex function applied to an average, and that is less or equal than the average of the collection of points we get when we apply the convex function first. So this is a not so complicated and kind of straightforward generalization of the property of convexity. The Jensen's inequality is intuitive and not complicated, and it has very strong consequences. As an example, for the Jensen's inequality, we recall another inequality for the integral, which is classical. This will be deduced from the Jensen's inequality for the case when the convex function is just the absolute value function on the real line. And applying the Jensen's inequality in this case just gives us that the absolute value of an integral is less or equal than the integral of the absolute value of a random variable. Now, the next step, or the next concept we want to use, and which is of tremendous importance in probability theory, is the concept of variance. The variance measures the mean quadratic variation, the mean quadratic deviation from a random variable from its mean. Its definition is got like this. So if you have a real valued random variable with expectation m, then you can compute, for each realization of randomness, you compute the difference between the payoff at that realization of randomness and its mean value, the mean value of x. You compute this quantity, you square, and you take the expectation of this. This is called the variance of x. Okay, let us give an example. Namely, we start out with the probability space corresponding to the uniform distribution on the unit interval. So omega fp is the unit interval equipped with its broad sigma field, and p is the Lebesgue measure. The random variable we want to consider here in this example is, say, the map that takes a chosen number between 0 and 1 and converts it into its square. The expected value then is the integral of x of omega integrated against the probability measure p over the set omega, which in our case is the unit interval. So we need to integrate the square function against Lebesgue measure, which is a third. For the variance, we compute this difference of the realization of the random variable and its mean. We square this and integrate. If we multiply out the square, we get x squared minus 2 times 1/3 times x of omega plus a ninth. And since the random variable x is the square function, this is omega to the fourth minus 2 times a third omega squared for x. and the plus 1/9, and these are simple integrals. It's 1/5 minus 2/9 plus 1/9, so the total number is 4/45. Very often we compute the variance of a random variable by just comparing the moments, as we say. So a moment of a random variable is just the expected value of a power of this random variable, and the lemma, simple lemma, which we often use for the computation of a variance, is that the variance of a random variable is given by the difference of the second moment of this random variable minus its expected value squared. So variance equals expectation of x squared minus the expectation squared. Why is this so? So that we just write out using m. If we just write m equals, or set m to be equal to the expectation of x, we write the variance of x as it's defined as the expectation of the difference of x and its mean squared. We multiply out the bracket inside the expectation. Now we have an expectation of a linear combination of certain quantities. So we write it as the corresponding combination of expectations. Here, the first term is exactly this second moment. Second term is, since m goes as a factor in front of the expectation, the second factor is 2m times the expectation of x, but the expectation of x is what we call m. So in fact, this is minus 2m squared. This is a minus 2m squared, and we add m squared to that. So in the end, we end up with expectation of x squared minus m squared, which is the claim. Okay, let's do an example. The example will be that of the exponential distribution. So assume that the random variable x is distributed according to the so-called exponential distribution, which is obtained by integrating with Lebesgue measure against the weight function e to the minus u, or the negative exponential function, or exponential negative of the negative function. So in other words, it's again the perturbation of the Lebesgue measure, but now with the weight function given by e to the minus u. So the picture is similar to the picture of the standard normal distribution, but now with a different weight function. Then it's a simple exercise to compute the expected value m to be 1, and the computation of that is similar to the computation that we do now for the square. So we know that the variance of x is given by the formula above. It's the expected value of x squared minus the square of the expected value. So if we believe that the expected value of x is equal 1, we compute now the expected value of the square, which by the general transformation formula then is just the identity function squared integrated against the law. The law is this weighted Lebesgue measure, and this is what we see here is a candidate for an integration by parts, where this function here, the e to minus omega, is considered to be the f prime, and this is the g function. So the integral of f of e to the minus omega is minus e to the minus omega. So that's why we get this boundary term, and then moving the derivative to the first factor here in this integral gives a 2 omega e to the minus omega, and this omega times e to the minus omega d omega integral is exactly the expression that we have to compute when we want the expected value of this random variable. So what is written here, this integral is exactly the expected value of x, which was claimed to be 1. So in the end, we see that the expected value of the exponential distribution squared is 2. So by the formula above, we obtain that the variance of an exponential distribution is 2 minus expected value squared, which was 1, so it's a 1. So we get a 2 minus 1, which is 1. So the conclusion is that the variance is 1. I recall a simple fact which we basically used already when we introduced the concept of an expected value for simple random variables, namely the fact that the expected value of the so-called indicator function of a set equals its probability. So recall, what is the indicator function of a given set E? The indicator function of a given set E is the function, or is the random variable, which assumes values 0 or 1, and it is 1 on those omega which belong to a certain event E, and it is 0 else. So the indicator function is a function or a random variable given by a measurable subset of omega. So if that's omega, and we have a certain subset E, then the indicator function is equal 1 on that set, and it is 0 elsewhere. Or in another picture, if that's cross-section view, so to say, of omega, and you have a certain subset E, then the indicator function would be a 1 here, and it would be 0 elsewhere. That's the indicator function, and or sometimes it's also called the characteristic function. Both terms are equally good. So that's the indicator or characteristic function, and then the expectation of the indicator function is just the probability of E, and the variance of the indicator function is the probability of E minus the square of the probability of E. This is a direct consequence of the previous formula, since the expectation of the indicator function, or let's call it the second moment of the indicator function, so the expectation of the indicator function squared, that's just the expectation of the indicator function itself, because the squaring a 0 is 0, and squaring a 1 is a 1, so applying the square function to the indicator function doesn't change it, and that is the probability of E alone, and that's why we arrive at this formula according to the general lemma that we had before. I recalled this simple fact because it will appear in the proof of the so-called Tchebyshev inequality below, which is a very important tool and very important fact for probability theory. It is used a million times everywhere. So the Tchebyshev inequality is a terribly important tool in probability theory, and it connects the probability of seeing something atypical, namely a realization of the random variable which is different from its expected value, with the variance as a measure how likely this deviation will be. So the statement is as follows: let x be a real valued random variable, and let m denote its mean. Then we can ask for the probability that the realization, that the output, the actual observed output of the random variable, differs from its mean by more than epsilon, where epsilon is an arbitrary positive number. And the statement is that this probability is bounded from above by the ratio of the variance of x and epsilon squared. So you can measure, or you can estimate the probability of seeing something other than the mean in a precise or in a concrete realization of the random experiment. You can bound this probability from above by the variance divided by epsilon square, when epsilon is your level of tolerance. In particular, if the variance of the random variable is 0, then the probability to observe any deviation from the mean in a concrete measurement is 0. Or in other words, a random variable with variance 0 will assume exactly its expected value with probability 1, which is, of course, the case that the random variable is not probabilistic at all, or is not random at all. It's just deterministic. It always assumes a constant value, which in this case, of course, is its expectation. The proof of the Tchebyshev inequality is very simple, and therefore I present it here. It goes as this. So if we introduce as the event E exactly those scenarios omega which produce an output of the random variable which is different, or which deviates from the mean by more than epsilon, then the probability which appears in the statement of the Tchebyshev inequality is exactly the probability of this event. In fact, the probability that we write in the Tchebyshev inequality, or what we write in the Tchebyshev inequality above, is just a short form of writing the probability for precisely this event E. And we now will give an upper bound for the characteristic function of this event E. Namely, if we evaluate the characteristic function of E on E, then this is of course 1. On E, the quantity x of omega minus m over epsilon is greater or equal to 1 by definition of E. So if omega, the little omega, if we consider a little omega an element from the set E, which is this event which we had just defined above, then the difference between the realization of the random variable x and such an omega towards the mean value is greater than epsilon, so therefore the ratio is greater than 1, and therefore the square of this ratio is also greater or equal to 1, which allows us to say that the indicator function 1 on E is dominated from above by this function on the right-hand side. In the complement of E, we have that the indicator function assumes the value 0, which trivially is bounded from above by this non-negative number on the right-hand side. So in total, this indicator function is bounded from above by this ratio everywhere, and hence we may also have the same relation for the integral, because the expectation as an operation is monotone. So hence the expected value of this indicator function is bounded from above by the expectation of the corresponding right-hand side. And if we write out what that means, it means that the probability, namely the expectation of the indicator, is bounded from above by the expectation on the right-hand side, and the expectation on the right-hand side is exactly the variance. That's the proof of the Tchebyshev inequality. We now present two highlights of classical probability theory, which is the law of large numbers and the central limit theorem. And in both statements, the concept of independence is of central importance. In order to understand the concept of independence, we recall the Bayes concept of a conditional distribution or a conditional probability of events. So for this, assume that we have a probability space and two events A, B, where we want to also assume that, for instance, A has strictly positive probability. Then we define the conditional probability of B given A as the ratio of the probability of the intersection of A and B with the probability of A. This can be understood as the relative probability of the event B in relation to the probability of A alone. That's our definition of conditional probability of B given A, when A has positive probability. In pictures, it would probably look like this. You have your set omega and two events A and B. And what you measure is the size of that piece of B, which belongs to A, as a subset of A. So you restrict your probability space to the event A alone, and you measure everything as a subset of A, and you normalize all these measurements by the total probability of A in order to obtain a new probability measure as a probability measure of A on A. So in a way, the conditional probability of B given A is the restriction, the normalized restriction of the measure P to the subset A. Now, according to this Bayes definition, you would call the event B independent of A when the probability of B given A is again the probability of B. So when this conditioning procedure does not change B. So you would call, that's the first definition, P of B given A when this is in fact P of B. When this is the case, this is what you would call in this situation you would call B independent of A. That's your first attempt to understand independence. But this concept of independence, if that were your concept of independence, it would be not symmetric with respect to the roles that the sets A and B play. And second, it would assume that the probability of A is strictly positive. And the next definition of independence takes away those problems and defines it in a symmetric fashion. So that's our definition. Two sets or two events A and B in a probability space are called independent if the probability of A intersected with B is in fact the product of the two probabilities. That's a symmetric definition of independence, and it does not assume that any of the two events is zero. Independence also is trivially given if any of the two events is zero. And we see that if A and B are independent, and if the probability of A happens to be strictly positive, then in fact we retrieve our Bayes style independence of B. namely in this case, in the definition of conditional probability of B given A, the enumerator is just the product of P and A and P and B. So we see that P of A and this expression cancels out and we get back P of B. So in fact, if A and B are independent in the sense of the definition just given, then the conditional probability of B given A is in fact just P of B. So this implies that the conditional probability of B given A equals in fact P of B if P of A is positive. Let us give a standard example for such an independence, namely we deal with the probability space describing the twofold toss of a coin, of a fair coin, which is described by the probability space of tuples, binary tuples. We're equipped with the power set as sigma field and the uniform distribution. Then we can talk about the event, for instance, of success in the first toss, which is comprised of the two tuples 1, 1 and 1, 0. And we have the event of success in the second run, which is the set of the two tuples 0, 1 and 1, 1. The probability of the event E1 is the probability of an event of cardinality 2 in a set of cardinality 4 for omega, so the probability of this is a half, and analogously for E2 we have the probability of 1/2. The event which is obtained by the intersection of E1 and E2 is the event that we have success in both rounds. That's a single element event consisting only of the tuple 1, 1. And as one of 4 possible events, this has probability 1/4. And now we see that this 1/4 is exactly the product of a half and a half, which is the product of the two individual probabilities. So therefore, E1 and E2 are independent. We now generalize this concept of independence of two events to the concept of independence of random variables. Namely, let omega fp be a probability space, and let x and y be two random variables which for simplicity assume values in the same state space. State space equipped with sigma field sigma. Then we call x and y independent if all possible pairs of pre-image sets are independent in the sense of the previous definition. Namely, if for all possible target sets, for all pairs of target sets in the sigma field sigma, the corresponding pre-image sets, which are events, are independent. If this is an E1 and this is an E2, then we want that pairs of such events E1 and E2 are independent when the sets E1 and E2 are obtained as pre-image sets under the map X and Y for pairs of target sets S1 and S2. So you see that this definition of independence of random variables is in fact a requirement on the collection of pairs of pre-image sets, where the pre-image sets are obtained by respective use of x and y of the two random variables which are supposed to be independent. Another way of saying this is that two random variables are independent if and only if all pairs of events that we can construct by evaluating x and y at the same time are independent. The following proposition yields reformulations of independence, which are straightforward abstractions of the just given definition of independence. The first statement is a consequence of independence of random variables, namely if x and y are independent, then all subsequent transformations of x and g alone by pairs of functions f and g which are measurable, then those resulting pairs of new random variables f of x and g of y are again independent. This is because the corresponding pre-image sets which we obtain by looking at f of x and g of y will be essentially of the same structure, or they will be even only a coarsening of the pre-image sets that we had discussed or that were occurring in the initial definition of independence. So we do not enrich the collection of pre-image sets by applying other transformations of x and y, and therefore the mutual independence of all these possible pre-image sets will be preserved. The second statement of the proposition is a reformulation of the independence in terms of the corresponding laws of the random variables. First of all, we want to understand what the joint law of the random variable x and y is. Namely, if we conduct the random experiment, which means we sample the realization little omega from omega, then we can do a simultaneous evaluation of the two random variables x and y. The simultaneous evaluation of the two random variables x and y yields a map from omega into the product space of S with itself. And if x and y were measurable, and if we equip the product space, the Cartesian product S with itself with the natural product sigma algebra, then this random variable xy, this joint random variable x and y, will be measurable. Now understood as a map from omega into the product space. And then we can talk about the law of this joint evaluation f, x and y, which will be a probability measure on the product space. In the probability measure on the product space is uniquely determined by specifying the measure on Cartesian products, so on rectangles in this product space. And a rectangle in this product space consists of a Cartesian product of two measurable subsets in the two different coordinates. So this set here is a subset of the product space, of the Cartesian product S with itself, where S1 and S2 are measurable subsets. So in a picture you would have that you have the product of S with itself, and then you have So probably would want to write it like this. So we have we have our space omega. Now we have the map which consists of the joint evaluation of x and y. And this is now a map which takes you to the product space of S with itself. And here you can ask for the probability of the joint evaluation of x and y to assume values in a rectangle which consists, or which is obtained by taking the contingent product of two sets S1 and S2 in the vectors. And the condition of x and y being independent now means that the joint law of x and y, so the measure of this rectangle in this product space, when measured with respect to the law of the joint evaluation of x and y, is nothing but the product of the lengths of the two sides which you measure in each component or in each factor with respect to the law of x and y alone. Whenever you have a measure on a product space which is of this rectangular structure, namely that whenever you measure the size of a rectangle, and the size of the measure of the volume of a rectangle is in fact just the product of the sizes of the corresponding side lengths or side intervals, then you call such a measure a product measure, and you write it in this tensor notation that the measure is in fact a tensor measure. So the statement here is that a pair of random variables x and y is independent if and only if their joint law is in fact a tensor product measure. And in the exercises we will give examples showing that this is by no means always the case for generic random variables x and y, which are defined in the same probability space. So this measure theoretic description of independence shows that the independence of two random variables is a property which can be formulated alone by looking at the joint law of x and y. So it's again a property of the law, but now the property of a slightly more complicated law, which is obtained by looking at the two random variables at the same time. So by evaluating these two random variables on each realization of randomness at the same time, which leaves a random variable in a more complicated state space, namely in the product of the state space of the two state spaces. The third reformulation, or the third statement of this proposition is a reformulation of independence in terms of expected values. So we can say that x and y are independent if and only if the expectation of all transformations of random variables by measurable real-valued functions, by pairs of measurable real-valued functions, when all these expectations of these products are the same as the products of the expectations. This property 3 is the one that we will use most of the times. And we will use it also in the law of large numbers and in the central limit theorem, in fact. So x and y are independent if and only if the following is true: whenever for all possible transformations of x and y, by means of pairs of real-valued functions which map the state space into the reals, so by real-valued observables, if you like, if then the expectation of the corresponding product random variable after transforming is nothing but the product of the two expectations of the two factors. That's a very useful way to describe expectations, and we shall use it later on plenty of times. And it can be easily understood if you consider the simple case when f and g are indicator functions for certain measurable subsets, S1 and S2, and then the expectations of these functions are nothing but probabilities. We know that the expectation of an indicator function translates into probability, and then we see that this formulation that we have here is nothing but a statement about probabilities of pre-image sets, and that is exactly the initial formulation of independence that we were starting with. And to come from this simple case, to deduce from this simple case to the general case when f and g are more complicated than just indicator functions, this is just an exercise in approximation of a complicated function f and g by a piecewise constant function defined through a linear combination of indicators. We now generalize the concept of independence of two random variables to the case of a family of random variables. Now assume we are given a probability space omega fp and a family of random variables which assume values in a joint state space S equipped with a sigma field sigma. Recall that such a situation was called a stochastic process before. So if you assume that we have such a family of random variables, we call this family of random variables independent if the following holds true. If we select some finite subset of indices, call it J, and if we select for each J in this finite index set J, we select some measurable target set Sj, and if we ask for the probability that the joint evaluation of all the random variables xj from this set J, capital J, produces values in the corresponding image set Sj for each random variable xj. If we ask for this event of joint behavior of the random variables xj when j ranges over this finite collection of indices, then the probability for this to happen should be the same as if we had computed the respective probabilities of evaluating the xj random variables alone and asked for the values assuming in the set of Sj and taken the product of this. Let us give two examples where such sequences appear. First example goes back to the probability space that we constructed in the previous session for the description of the iterated application of a random number generator to produce an infinite sequence of random numbers. So omega was this infinite sequence space equipped with the Borel sigma field which was generated by these cylinder sets, and the probability measure was the extension of the uniform probability measure on cylinder sets to the corresponding sigma field. And then we can define a sequence of random variables xk, which is each for each k is defined as follows. So the random variable xk evaluated on an infinite sequence omega just evaluates the kth entry of that sequence. So xk is just a projection onto the kth element or onto the kth coordinate of that sequence. I claim that this is an independent sequence. These xk sequence is an independent sequence of random variables. Why is this so? Well, if we take a finite collection of indices, j1, j2, j3, and so forth, and ask for the probability that at these indices, the sequence that we evaluate has certain prescribed values, namely at index j1, we observe the number k1 as entry, at index j2, we observe k2 as entry, and so forth, then this probability is in fact a probability which involves a cylinder set, namely we evaluate only infinitely many coordinates. This is precisely an event which is of a cylinder set structure, and therefore this is computed by using the very definition of the P on cylinder sets, which in our case here was defined as the uniform distribution on the corresponding truncated set of sequences, or sequences of a set of truncated sequences. And here we can evaluate this precisely in order to convince ourselves that here, in fact, this product rule applies. So, in fact, this infinite sequence is independent. The second example looks at first sight quite different, but in the end it turns out to be almost the same. But namely, we consider the probability space for the uniform distribution on the unit interval that we had discussed already now several times. And before we define this sequence of random variables xk on this space, we recall that each number in the unit interval has a unique representation as a power series where we take powers of 1/2 or negative powers of 2. And then we can develop each number between 0 and 1 as a power series of these negative powers of 2 with coefficients 0 or 1. Geometrically, it describes that we have a choice to make at each level k. So at level k equals 1, say, we have to make a choice whether our number omega lies to the right or to the left of the number 1/2. This is the question whether C1 is 0 or 1. And then once we have made a choice here, we can subdivide the next two half unit intervals into subsequent half intervals or intervals of size 1/4, and we have to make the next choice whether our number omega lies to the left or to the right of this next intermediate intersection point or cut point, and so forth. So we have a sequence of choices to make, and this sequence of choices we make is encoded by this sequence of digits 0 or 1 corresponding to this development of this, or the representation of the number omega by negative powers of 2. So we have the one-to-one map between omega and this sequence of CL or CKs, and correspondingly our choice or definition of a random variable xk is exactly the digit in the kth digit in this expansion. And then it's a not too difficult exercise to convince yourself that these xk's are in fact an independent infinite sequence of random variables. The next definition and final definition which we want to give before we state the law of large numbers is this. A sequence of random variables which is independent is also called identically distributed, independent identically distributed, which has the abbreviation IID, if it is independent and all laws of the random variables which occur are the same. The previous two examples were exactly of this nature. Each of the corresponding random variables xk had the same law. Finally, we can state the law of large numbers in weak form, which shows in another way why the expected value of a random variable is important and why it appears naturally when we conduct measurements, for instance. The statement is as follows. If we have a sequence of IID random variables, and if we denote by m the expected value, which will be always the same for all of those random variables, and if v is the variance, which is supposed to be finite, then we can evaluate these random variables one after the other, and we can compute the mean value of the first n evaluations of this random variable. This will be a random number. So we have a sequence of random events or random variables, and we compute the arithmetic mean. And the law of large numbers says that this arithmetic mean will be almost the expected value of the random variable if we compute it in the statistical sense. So the mean value of this first n measurements is close to this deterministic number, which is the mean value or the expected value of this individual random variable, and we can give an upper bound for the probability of measuring a deviation. So for tolerance level epsilon, which is positive and arbitrary, we ask what's the probability that there is a deviation of the arithmetic mean of the first n rounds from the mean value, from the deterministic mean value, by more than epsilon. And the probability for this is bounded from above by a constant, namely v, divided by n over epsilon squared. In particular, we obtain that for n tending to infinity, the probability of a deviation of the arithmetic mean from the deterministic value is converging to 0. The proof of this statement is not so complicated anymore once we have done all the preparations. Namely, let an be the sequence, or let an be the quantity which is exactly this arithmetic mean of the first n rounds. Then we can compute the expectation of this quantity, which will be just the corresponding mean value of the individual expectations. Each expectation alone, by the assumption that all xi have the same distribution, is m, so we get the mean value, the arithmetic mean of n instances of the same number m, which is of course n. Then we can compute the variance of this quantity an. The variance, as we know, is the expectation of the square of the difference of an towards its mean. The mean we had just computed is m. If we write out what an is, it's the mean value of the xi, and we can combine this with this arithmetic mean operation on the m, so we write it as the arithmetic mean of the difference of the individual xi towards the m. This is now the expectation of a square of a sum. If we expand the square, we get the expectation of a double series with two indices. This double series can be decomposed in this sum when the two indices differ. So the off-diagonal part of this double sum is written out here, and then we have the diagonal part of this double sum when the indices coincide. when the indices I and j are different, then the independence of xi and xj kicks in, which allows us to write this expectation of the product as the product of expectations. This is the step from here to there. Now each individual expectation is 0, because if we write out what this means, this is we take the expectation of xi minus m. This is the same as if we had computed the expectation of xi and subtracted m, but the expectation of xi is just m, so therefore we obtain a 0 at each of those factors. So in particular, this sum is 0, and the expectation of this diagonal part is the sum of the expectation of the squares of xi minus m, but this is exactly the variance of individual xi, but they are all the same by identical distribution. So we get each time in this sum we get just the variance again and again. So we obtain that this is the sum over the variances, where we had the prefactor 1 over n square, which was coming from the mean value operation, the arithmetic mean, which in the variance is squared such that it appears as a 1 over n squared in front of the expectation. So we have this 1 over n squared in front of the sum, which cancels with the n-fold summation of the v terms in the sense that 1 over 1 n factor is cancelled, and we end up with v over n. So the variance of this quantity an, which we had just introduced, is v over n. Sometimes this is also called the Biennami identity. And hence we can apply the Tchebyshev inequality to this random variable an, which says that the probability of an being away from its mean value m by more than epsilon is bounded from above by the variance of an divided by epsilon square, and the variance of n we had just computed, it is v over n. And we see that this quantity converges to 0 when n tends to 0. The previous result was called weak law of large numbers because there is a better version called the strong law of large numbers, which involves an amplified type of convergence of this sequence of observations. It will then ultimately state that under appropriate conditions, this sequence of arithmetic means of the outcomes of the random variables xk will even converge almost surely to the mean value. We will discuss this stronger version of the law of large number a little later using the theory of martingales, which we will develop after the theory of Markov chains. Now, as the last result of today, of this session, I want to present the central limit theorem without proof, but since the normal distribution will appear later as a building block for the construction of Brownian motion as a model of diffusion of a molecule in space, say, I want to mention at least why the normal distribution is a natural object in the real world, and this is mathematically substantiated by the central limit theorem. It also deals with the sequence of IID random variables, and also deals with an average that I can take when I observe the iterated realizations of this sequence of random variables. Namely, that xk be an IID sequence of real valued random variables whose expected value is denoted by m, and assume that the variance of this random variables is finite, call it v. Then we can compute an average value of deviations of xk from its mean value. So we take the sum of deviations of the realizations of the random variables xk from the mean value. We sum them up, these deviations, and we divide by a certain normalizing factor in front, which is chosen in such a fashion that the variance of this quantity here, which appears in the statement, which we call psi n, the variance of this quantity is exactly 1. So this prefactor here, which is in formulas is 1 over square root of n times v, where n is the number of observations that you need to produce this quantity. That's just the number of summons in this sum. And v is the variance of each of those random variables xi. So if you take this sum and if you normalize it properly, then this sequence will converge to a standard normal distributed random variable in the following sense. That whenever you ask yourself about the distribution of this random variable, maybe you ask what's the probability, for instance, that for any given threshold level t, this number is below the threshold value t, then this probability for n tending to infinity converges to the corresponding probability that you would observe for a standard normal distributed random variable. In this sense, the statistical properties of this properly normalized sequence of random variables converges, or the statistical properties converges, the statistical law, the description of this random variables converges to the description given by the standard normal distribution in this sense. That's the statement of the central limit theorem. The remarkable thing about this is that the precise nature of these individual xk is almost unimportant or completely neglected. The only information you need for this to be true and for this to hold is information on the mean value of these individual xi and its variance. So the statement will always be the same regardless the precise nature of the random variables xi, wherever they were taken from, and whatever further details characterize their behavior. The only matter that really comes into play for the central limit theorem to hold is the mean and the variance. And then if you properly form a sum of these sums of xk, then this properly standardized and normalized sequence of sums of these xk will converge to a standard normal distributed random variable, in the sense that the probability or the distribution of the distribution function, you could also say this, that the distribution function of this sequence of random variables converge pointwise to the distribution function of a standard normal random variable. So remark this random variable psi n, of which this effectively is a statement. This random variable psi n is made in such a fashion that it is effectively the sum of the individual xk, but the sum is shifted by an additive shift and finally also scaled by a multiplicative scaling, such that this that this resulting sum psi n after shift and after scaling has expectation 0 and variance 1. This is the same as for the standard normal distribution. The standard normal distribution also has expectation 0 and variance 1. So you shift and scale this sum of individual pushes of individual xk just in order to match the first two moments, as we would say, of the standard normal distribution, namely to have the same mean value and the same variance as the standard normal distribution. And then the central limit theorem already kicks in and tells you that in terms of distribution, you have convergence to a standard normal distributed random variable. That's a very massive and a very powerful statement, and it says in an intuitive fashion that whenever you have a random quantity which can be understood as the sum of many, many independent underlying random quantities, then this random quantity will already behave like a standard normal distribution. And that's why you can observe standard normal distributed random variables so often in nature, because many phenomena which you observe will in fact be phenomena which are aggregate phenomena of randomness at a lower level, and therefore you are effectively looking at a normally distributed random variable. For simulations of this, you can look up on the internet using the search words Galton board. This is a nice school experiment that you may have seen at school or somewhere else. There are also videos everywhere on the internet which tell you, or which in a quite captive fashion show that this is not fiction, but it really appears in science and in nature. This concludes our very quick rush through the most fundamental concepts of classical probability theory. And now, finally, we can start with the discussion of the real matter of our course, namely stochastic processes.